in set B. Now we've kind of talked about most of the stuff in this formal definition, that it's a rule of correlation. A rule of correlation. Here's our rule. Here's how they got paired up. What we haven't spent a lot of time talking about is this exactly one. That each element in set A is paired with exactly one element in set B. So let's go through this in a little more detail. And I'm going to show you some pictures here. We're going to go back to some other representations of functions, but it's probably easier to see if we look at what's not a function. Okay, so things that are not representations of functions. We'll take one of our forms was a picture where I had my domain and my range. Or if we look at our list up here, we could call this set A and set B. I'm going to start very simplistic and show you, if I put a 2 into my machine, we're going to go back to the machine again. When I put a 2 in, I should get the 3 out. Every time I pick up a 2 and plop it in, I should get a 3 out. That's exactly 1. So if I have something that's showing me that one time I put a 2 in, and I got a 3, and the next time I put a 2 in, I got a 1. This is a representation of something that's not a function, because I do not have exactly one element that the 2 is paired with. I have more than one. So that won't work. In our other representations, for example, if we have a set of ordered pairs, if I have a set showing that the 2 is getting paired with the 3, and we had a 1 paired with a 0, and I put the 2 in again, and this time I get a 1, you'll see that the 2 is getting paired one time with the 3, one time with the 1. It's not exactly 1, I have more than 1. This is something that is not a function. And at this point, let me just show you one other set that I don't want you to get it confused with. Notice the difference here. I do have a repeating number, but what's repeating here is the output number. The 1 is getting paired with a 2. Every time we see a 1, it's getting paired with exactly one other number. -3 is getting paired with a 2. It's okay, because the -3, every time I put it in, I'm getting a 2 out. The 5, every time I put it in, I'm getting a 2 out. So even though I have a repeating number, this one's different. This one does represent a function. Pictures, or our graphs, when we look at functions, let's take an example. If I look at a graph and I'm looking to see that each number in my domain along the x is paired with exactly one y, what I'm doing is I'm checking to see, here's an x value, I'm going to go check the graph, has exactly one y. This, and as I go across my graph and check at different locations, I see that every x is paired with only one y. This, what I just demonstrated, was the vertical line test. We use the vertical line test on a graph to determine whether it's a function or not. An example of one that is not a function then, where it wouldn't pass a vertical line test, would be something like this. When I draw my line, my vertical line touches in two places. What that means is that my x value here is getting paired with more than 1. Not exactly 1, more than 1. So this is a representation of something that is not a function. When we deal with functions, another thing that we're going to spend some time looking at is we're going to spend some time looking at the domain. The domain is going to become a little more important to us as we go through. And the domain of a function can sometimes be restricted. What we're going to be doing as we program our machines and start working with our function machines is we're going to have to look at some of those restrictions on the rule or on the function. And here's a couple examples. So example 1, place where we have a restriction is when we are dealing with radical functions. Hopefully at this point you've worked with some radical functions and you know that in order to stay in the real number system, I'm going to be restricted on what numbers I can put in for my x. In this case, you would know that I really am not going to be able to put negative numbers into my function here for x. Otherwise, I'm going to end up in a complex number system, and we're not going to go there right now. We're just dealing with real numbers. So in order to show that this domain is restricted, I need to let people know that my domain is going to be positive numbers. That means x has to be greater than or equal to 0. In interval notation, we're going to show that that means that my domain is going to go from 0 to infinity and deal with just positive numbers. Another place that you're going to have to watch for restrictions is when you're dealing with rational functions. So example 2, let's get another example here. Rational functions, something that looks like this. So in a problem like this, we know that when we're dealing with rational functions and rational expressions, we cannot have a 0 in the denominator. So this is another place where we're going to be restricted. We can't allow zeros in the denominator, so we're going to have to tell people not to put numbers in for the x that would give us a 0. So in this case, what we're saying is that our domain is restricted. Our domain, we can use all numbers, all real numbers, except for x cannot equal -1. To show that again in interval notation, I would show that I can use all numbers from -infinity up to -1. And then, but not including -1. And then again from -infinity, or -1, not including -1, up to positive infinity. All right, the last thing that we're going to look at in this introduction to functions is a little more detail on function notation. So we're going to go back to looking at function notation, and I want to just real quick remind you of our function machine here. That this machine was named f. Our function notation shows that we're dealing with f of x equals x plus 1, where we have our variable and our rule. So let's look at a few more detailed examples of function notation. Let's take a new function. We're going to reprogram our machine. So we'll take a quadratic function. And what we're going to do is show how to work in function notation without the picture and without the graph, just using our algebra. So if we're asked to find f of 2, what that means is that we're taking the 2 and we're going to put it in place of the x. Wherever we see the x, we're going to plop in a 2. And then we evaluate our function from there, following all of our order of operation rules. 4 minus 6 plus 1. And I can represent this then, saying that f of 2 equals negative 1. When I put in a 2, I'm going to get out a negative 1 for this function. No matter what the number is, no matter what is represented in this parenthesis, is what I'm going to be plugging in, even if it's another variable. So in this case, instead of actually plugging in a number, I'm plugging in a different variable. And sometimes our answers will still be expressions like this, if I'm plugging in a variable. Sometimes I might be plugging in a combination of things. I might be plugging in a whole nother expression. So when this happens, we're going to show that we are taking that entire expression and running it through our machine. So that every place there was an x, I'm replacing it with the x plus 2 in this example. Now, in dealing with these, now we have to evaluate it. In dealing with these, please be careful with your squares here. This isn't x squared plus 4. I'm going to be a little more detailed just so that everybody remembers this.